Welcome to tonight's journey into the deep ocean. Close your eyes and relax your tired muscles. The busy events of your day are now behind you. It is time to find peace in the quiet dark. Take a slow, deep breath in through your nose. Let the cool air fill your lungs completely. Release the breath slowly through your parted lips. Feel the tension leaving your shoulders and your neck. Allow your arms to rest heavily at your sides. Tonight we travel far away from the noisy surface world. We are going to a place of absolute stillness. Your mind can rest as we explore the abyss. The world above the waves is fading into complete silence. Only the gentle rhythm of the sea remains now. Allow yourself to sink into this comforting nighttime atmosphere. You are perfectly safe on this peaceful underwater expedition. Let my voice guide you into the deep shadows. We are embarking on a very special scientific voyage. Our destination lies hidden beneath millions of tons of water. We step inside a specialized deep-sea submersible vehicle. The heavy steel hatch closes with a reassuring sound. We are completely sealed inside a comfortable protective sphere. The interior lights glow with a soft amber hue. Quiet humming from the life support systems fills the cabin. This steady mechanical hum is incredibly relaxing to hear. We detach from the mothership and begin our dive. The submersible slips smoothly beneath the dark ocean surface. We are descending into the vast Pacific Ocean. This is the largest body of water on Earth. It covers more than 30% of the planet. Our specific target is the East Pacific Rise. This structure is a massive underwater mountain range. It represents the most densely populated hydrothermal vent area. This geological wonder remains largely unseen by human eyes. We drop below the surface and continue our descent. The warm surface waters quickly give way to cold currents. Light begins to filter out as we sink deeper down. The bright blue water turns into a deep twilight shade. We are heading towards specific coordinates in the ocean. Our vessel approaches 9 degrees 50 minutes north latitude. We cross 104 degrees 17 minutes west longitude. This precise location places us far off the Mexican coast. Thousands of miles of empty ocean surround our current position. No coastal lights can reach this isolated marine wilderness. We are entirely alone in this vast aquatic space. The nearest dry land is many hundreds of miles away. Above us, the ocean's surface is a distant memory. Below us lies an uncharted realm of geological mystery. Oceanographer Robert Ballard helped pioneer exploration in these regions. His early expeditions revealed the hidden secrets of the deep. We follow in the wake of these great scientific explorers. Our navigation systems track our steady downward progress. Digital screens display our exact latitude and longitude coordinates. The numbers change slowly as ocean currents drift us slightly. Small thrusters correct our course with gentle bursts of power. We maintain a precise trajectory toward the mid-ocean ridge. The gentle rocking motion of the waves is gone now. We are gliding through a perfectly calm liquid universe. Your body feels light and completely relaxed in your seat. We continue our slow descent through the dark water column. The sunlight completely vanished many hundreds of meters ago. We are now passing the 1,000-meter depth mark. This marks the beginning of the dark midnight zone. No solar photons can penetrate this deep oceanic water layer. The water around us is a pure and inky black. Bioluminescent creatures occasionally flash in the dark, empty void. They look like tiny shooting stars in the night sky. We sink further down toward the distant ocean floor. Our depth gauge reads 2,000 meters below sea level. The target depth is exactly 2,500 meters. This equals roughly 8,200 feet straight down. It takes several hours to reach this profound ocean depth. The slow downward journey gives your mind time to rest. Imagine yourself floating weightlessly down through the dark water. Gravity feels gentle and slow in this vast liquid realm. The altimeter pings softly as we approach the rocky bottom. Sound waves bounce off the unseen seafloor far below us. The returning echoes tell us exactly how high we are. We are now just 500 meters above the ridge. We rely entirely on advanced sonar and precise mathematical calculations. The depth gauge slowly ticks past 2,400. We are entering the final stage of our long dive. The physical conditions at this depth are incredibly extreme. The weight of the ocean creates massive hydrostatic pressure. Every single square inch experiences an immense crushing force. The pressure is about 250 standard atmospheres. This is 250 times the normal surface pressure. A standard styrofoam cup would shrink to a tiny thimble. Human bodies could never survive this harsh environment without protection. Our specialized titanium submersible keeps us perfectly safe and warm. The thick metal hull easily withstands the heavy ocean weight. You are completely secure inside this advanced pressure sphere. The extreme pressure changes the physical properties of the water. It prevents the superheated vent fluids from boiling immediately. This physical anomaly creates a highly unique chemical environment. The dense water feels thick and heavy outside our window. Sound travels much faster in this highly pressurized liquid medium. The acoustic environment is strange and deeply resonant down here. The intense pressure also affects the dissolution of essential minerals. Calcium carbonate dissolves much faster in these deep ocean conditions. This means no regular seashells can exist at this depth. Only specially adapted organisms can build shells in this zone. We are visitors in a world ruled by crushing physics. Yet inside our cabin, the air pressure remains perfectly normal. You can breathe easily as we explore the deep sea. We turn on the bright exterior lights of our submersible. Powerful LED beams cut through the eternal oceanic darkness. The water is filled with tiny drifting white particles. Marine snow falls continuously from the surface waters far above. These organic flakes sustain the fragile deep ocean food web. Without our lights, the darkness would be absolutely complete. The sun has never touched this ancient black volcanic rock. The ambient water temperature is bitterly cold in this zone. External thermometers register a constant 2 degrees Celsius outside. This is just slightly above the normal freezing point. Cold ocean currents sweep slowly across the barren rocky terrain. The chilling water flows down from the distant polar regions. It creeps along the abyssal plain over many long centuries. This freezing fluid constantly bathes the hot volcanic ridge system. The stark contrast between fire and ice defines this realm. Heat from the Earth's interior warms the rocks slightly, but the vast ocean quickly absorbs this geothermal thermal energy. The cold water dominates the environment just meters away. There is nothing to fear in this quiet, untouched wilderness. The deep sea is a place of profound natural tranquility. Generations of deep-sea biologists have marveled at this stark environment. Scientists like Holger Janisch studied these extreme temperature gradients. Their work revealed how life adapts to the freezing dark. The history of ocean exploration changed in the late 70s. Scientists turned their attention to the vast Pacific Ocean floor. Plate tectonic theory was gaining widespread acceptance at this time. Researchers wanted to examine the mid-ocean spreading centers directly. The East Pacific Rise became their primary geological target. This massive underwater mountain range stretches across the southern hemisphere. It marks the boundary between diverging massive tectonic plates. Magma rises from the mantle to fill the widening gap. This continuous volcanic process creates brand new oceanic crust. Geologists suspected this area held profound secrets in the dark. The story truly begins with a precursor expedition in 1977. Scientists visited the Galapagos Rift near the equator. They found warm springs seeping from the fractured basaltic seafloor. The water temperature there measured around 20 degrees Celsius. Strange biological communities surrounded those gentle warm water seeps. Researchers found giant clams and pale blind crabs in the dark. However, they did not find the source of the immense heat. The geological models predicted much higher temperatures at the spreading axis. The search for the true thermal vents had to continue. The scientific community needed to find the primary hydrothermal source. In the spring of 1979, a new mission began. The project was officially named the Rivera Submersible Experiments. Scientists simply referred to this massive undertaking as Project Rise. Their precise destination was 21 degrees north latitude. The exact longitude was 109 degrees west. This location sits off the coast of the Baja California Peninsula. The ocean depth at this specific site exceeds 2,600 meters. 3 distinct research vessels formed the core of the expedition fleet. The research vessel Melville sailed from Scripps Institution of Oceanography. The research vessel Gillis joined from the University of Miami. The tender ship Lulu carried the deep submergence vehicle Alvin. Lulu was a slow and cumbersome twin-hulled catamaran vessel. It belonged to the Woods Hole Oceanographic Institution in Massachusetts. The ship provided a floating launch platform for the small submarine. Living conditions aboard the Lulu were notoriously cramped and difficult. Yet the scientific crew remained focused on their historic mission. Alvin was a marvel of deep ocean engineering at the time. Its core was a perfectly spherical titanium pressure cabin. This thick metal shell protected the crew from crushing abyssal pressure. The submarine could safely carry 1 pilot and 2 scientific observers. Mechanical manipulator arms allowed the crew to collect physical geological samples. Thick acrylic viewports provided a limited window into the eternal darkness. The expedition was led by Chief Scientist Fred Speece. Other prominent researchers included Ken MacDonald and Robert Ballard. French scientists Thierry Juteau and Jean Francheteau also joined the team. Biologist Frédéric Grassel prepared to study any potential marine life. This international collaboration brought diverse geological expertise to the mission. The first phase of the operation required extensive acoustic mapping. The research vessel Melville deployed a sophisticated deep-tow instrument package. This heavy device was lowered on a long armored steel cable. It glided slowly just a few dozen meters above the seafloor. Side-scan sonar painted a detailed acoustic picture of the rugged terrain. The instrument also carried highly sensitive water temperature sensors. The deep tow system detected several tiny thermal anomalies in the water. These slight temperature spikes indicated active geothermal venting below. The scientists needed visual confirmation of these unseen geological features. They deployed a specialized camera sled known by the acronym ANGUS. ANGUS stood for Acoustically Navigated Geological Underwater Survey. It was a heavy steel frame packed with deep-sea cameras. Powerful strobe lights illuminated the pitch-black ocean floor. The sled was towed blindly across the jagged volcanic landscape. It automatically captured one color photograph every 10 seconds. Late one night, the ANGUS temperature sensor recorded a massive spike. The water temperature jumped drastically in a matter of seconds. The crew quickly winched the heavy steel sled back to the surface. They carefully extracted the wet photographic film from the pressure housings. The scientists developed the long rolls of film in a darkroom. They gathered around a bright light table to examine the fresh images. The photographs revealed a bizarre and beautiful alien landscape. Massive mounds of colorful mineral deposits covered the gray basalt. Dense clusters of giant tubeworms thrived among the rocky spires. This photographic evidence confirmed the presence of an active hydrothermal field. The team immediately prepared the Alvin submersible for a targeted dive. The historic descent occurred on April 21, 1979. This was officially recorded as Alvin Dive number 914. Pilot Dudley Foster guided the small white submarine beneath the waves. Scientists Cherry Juteau and William Normark sat cramped inside the sphere. The descent to the ocean floor took 2 long, quiet hours. Sunlight completely vanished after the first few hundred meters of depth. The surrounding water grew progressively colder as they sank deeper. The ambient temperature eventually dropped to a mere 2 degrees Celsius. The pressure outside the titanium hull increased by 1 atmosphere every 10 meters. Condensation formed on the cold metal walls inside the submarine cabin. The crew wore heavy wool sweaters to stay warm in the freezing depths. The submarine finally reached the bottom at 2,600 meters. Foster turned on the powerful exterior incandescent lights. The beams cut through the absolute darkness of the abyssal plain. They navigated slowly across a landscape of fresh pillow lavas. These bulbous rock formations were created by rapidly cooling magma. The submarine approached the coordinates of the massive thermal anomaly. The water outside the acrylic windows suddenly became cloudy and distorted. A strange shimmering effect blurred their view of the ocean floor. This optical illusion resulted from the mixing of different water temperatures. A massive geological structure slowly emerged from the dark, murky water. It was a towering mineral spire rising from the basaltic crust. Dark, opaque fluid billowed violently from the top of the chimney. It looked exactly like a factory smokestack belching dark pollution. This was the very first black smoker ever seen by human eyes. The dark plume was not actual smoke, but mineral-rich liquid. It poured into the freezing ocean at an astonishing velocity. The surrounding water was thick with dark suspended particulate matter. The scientists were eager to measure the exact temperature of the fluid. Alvin slowly extended its mechanical titanium arm toward the dark plume. The arm held a standard oceanographic electronic temperature probe. This delicate instrument was designed to measure slight warm water anomalies. The probe carefully entered the violent upward flow of the black smoker. The digital temperature dial inside the submarine instantly maxed out. The reading hit 32 degrees Celsius and completely stopped registering. Then, the protective plastic casing on the metal probe began to melt. The scientists quickly realized the fluid was unimaginably hot. They had to abort the temperature measurement to save the equipment. The melted probe was brought back to the surface ship for inspection. Engineers aboard the Melville had to design a completely new measuring device. They constructed a specialized thermocouple wrapped in thick thermal tape. Alvin returned to the Black Smoker field a few days later. They inserted the newly constructed thermocouple directly into the venting fluid. The digital display inside the cabin registered an astonishing number. The water temperature was exactly 350 degrees Celsius. This extreme heat was hot enough to melt solid lead. At sea level, water boils at 100 degrees Celsius. However, the deep ocean environment completely changes the physical rules. The immense weight of the water column exerts crushing hydrostatic pressure. This extreme pressure physically prevents the superheated water from boiling. The vent fluid remains a stable, superheated liquid state. The chemical composition of the black smoke was equally fascinating. The dark fluid consisted entirely of dissolved heavy metal sulfides. Deep cold seawater seeps down into the fractured oceanic crust. It travels close to the shallow magma chambers beneath the ridge. The extreme heat strips magnesium and sulfates from the seawater. The hot acidic water then leaches heavy metals from the surrounding rocks. This buoyant, toxic fluid rapidly rises back to the ocean floor. It shoots out of the vent into the freezing abyssal water. The sudden drastic cooling causes the dissolved metals to instantly precipitate. Iron, copper, and zinc form tiny dark solid mineral particles. These precipitating minerals slowly build the tall vent chimneys over time. The structures can grow several centimeters in a single day. Some mineral chimneys at the East Pacific rise reach immense heights. They eventually collapse under their own massive, unstable weight. The fallen debris creates vast mounds of valuable polymetallic sulfides. The extreme heat and toxic chemicals seemed utterly hostile to life. Yet the area around the smokers teemed with bizarre unknown organisms. Giant clams with stark white shells clustered in the warm crevices. Blind galethide crabs scavenged among the towering porous mineral spires. Scientists discovered a completely new species of deep-sea polychaete worm. They named this remarkable creature the Pompeii worm, or Alvinella pompeiana. It lives inside papery tubes attached directly to the smoking chimneys. The worm survives extreme temperature gradients along its small fragile body. Its tail rests in boiling water while its head remains freezing cold. Sunlight could never reach this deep, isolated benthic environment. Photosynthesis was physically impossible in the absolute darkness of the abyss. The foundational energy source for this ecosystem had to be different. The answer lay in the toxic hydrogen sulfide gas billowing upward. Specialized microscopic bacteria process the hydrogen sulfide from the vent fluid. They use pure chemical energy to produce complex living organic matter. This biological process is known in science as chemosynthesis. It forms the foundational base of the entire hydrothermal food web. The giant rifsha tube worms lack both a mouth and a stomach. They rely entirely on symbiotic bacteria living deep inside their bodies. The worm's bright red plumes absorb oxygen and toxic hydrogen sulfide. The internal bacteria convert these raw chemicals into food for the host. The discovery at 21 degrees north changed biological science forever. It definitively proved that complex life could thrive without the sun. Biology textbooks around the world had to be completely rewritten. It vastly expanded our understanding of planetary habitability and evolution. The East Pacific Rise event sparked new theories about extraterrestrial life. Scientists began to look beyond our own familiar blue planet. Moons like Europa and Enceladus might harbor similar hidden subsurface oceans. Deep hydrothermal vents could potentially exist on distant frozen celestial bodies. The expedition also revolutionized our fundamental understanding of ocean chemistry. The entire volume of the global ocean circulates through the crust. This massive hydrothermal plumbing system regulates the chemical balance of seawater. It removes certain common elements and adds massive quantities of others. The legacy of the 1979 expedition remains unparalleled. The successful collaboration between different institutions yielded truly unprecedented results. The East Pacific Rise became the most intensely studied ridge system. It continues to draw dedicated researchers from all over the globe. Following the initial discovery, many more research ships visited the area. Advanced remotely operated vehicles eventually replaced the heavy-towed camera sleds. High-definition video cameras captured the smoking vents in stunning detail. Robotic arms carefully collected delicate biological samples for laboratory analysis. The scientific community mapped a long segment of the volcanic ridge. They found multiple active vent fields scattered across the dark seafloor. Each new site revealed unique biological communities and geological formations. The East Pacific Rise proved to be the most dense hydrothermal region. Magma chambers sit extremely close to the crustal surface in this area. This shallow heat source drives the intense, continuous hydrothermal circulation. Yet the fundamental, quiet mystery of the deep ocean remains intact. The black smokers continue to vent their ancient geothermal heat. The mineral spires grow silently in the freezing, crushing darkness. The Pompeii worms cling tightly to the edges of boiling water. The unique ecosystem sustains itself in perfect, isolated, dark equilibrium. The deep ocean currents drift slowly past the massive sulfide chimneys. The ambient temperature remains stable across the vast dark abyssal plain. The heavy water column acts as a comforting, silent liquid blanket. The profound mysteries of the deep sea slowly fade into shadows. Scientific discovery brings gentle light to the darkest corners of the earth. The continuous cycle of deep ocean chemosynthetic life goes on undisturbed. The magma chambers pulse quietly beneath the thin oceanic crust. The massive tectonic plates continue their slow, relentless drift apart. The East Pacific Rise stands as a silent monument to planetary power. It remains a hidden world of extreme heat and eternal night. The memory of that first historic dive lingers in the cold currents. The melted temperature probe remains a symbol of human scientific curiosity. We continue to learn from the silent depths of the Pacific. The ocean keeps its oldest secrets safe in the freezing dark. The gentle hum of the earth resonates through the dense water. Rest now, as the deep sea continues its endless, quiet work. The East Pacific Rise represents a massive divergent tectonic boundary. Here, the Pacific Plate separates from the Cocos Plate. This continuous separation occurs deep beneath the dark ocean surface. Farther south, the Pacific Plate diverges from the Nazca Plate. These immense tectonic plates slowly drift across the Earth's mantle. Tremendous geological forces drive this silent underwater movement every day. Deep within the mantle, superheated rock slowly rises upward. This ascending mantle material creates a continuous magma reservoir. The magma chamber sits just beneath the thin ocean crust. Liquid rock pushes against the solid boundaries of the seafloor. The pressure forces the oceanic crust to split apart. Long, deep fissures form along the central ridge axis. Molten rock erupts through these cracks into the freezing water. This constant volcanic activity builds entirely new oceanic crust. Scientists monitor these tectonic shifts with incredible precision today. Sonar mapping reveals the vast scale of this underwater mountain. The ridge stretches thousands of miles across the Pacific Ocean. It forms a crucial part of the global mid-ocean ridge. Geologists classify this region as a fast-spreading mid-ocean ridge. The tectonic plates move apart at remarkable geological speeds. Measurements show a separation rate of 15 centimeters annually. This translates to about 6 inches of movement every year. Such velocity makes it the fastest spreading ridge on Earth. By comparison, the mid-Atlantic ridge moves much more slowly. Atlantic plates separate at merely 2 centimeters per year. This rapid Pacific spreading creates a distinct topographical profile. Slow ridges usually feature deep, steep-sided central rift valleys. The East Pacific Rise lacks a deep central rift valley. Instead, the rapid magma supply creates a broad, elevated summit. The ridge profile looks like a gently sloping underwater dome. The summit region spans several kilometers across the ocean floor. A very narrow axial trough marks the exact spreading center. This tiny trough measures only tens of meters in width. Fresh lava constantly fills any deep depressions that try to form. The high spreading rate prevents the crust from cooling quickly. A shallow magma lens exists just 2 kilometers below the seafloor. This extreme proximity to magma keeps the local crust unusually warm. Heat flows constantly outward from the interior of the Earth. Fresh basalt forms the primary foundation of this new crust. When hot magma meets seawater, it cools almost instantly. This rapid quenching creates unique geological formations called pillow lavas. Pillow lavas look like smooth, rounded tubes of dark rock. They stack upon each other in massive, interlocking mounds. A glassy exterior shell covers each newly formed basalt pillow. This volcanic glass forms because the minerals cannot crystallize fast. Beneath the glass, the basalt displays a fine-grained crystalline texture. In areas of higher eruption rates, sheet flows dominate the seafloor. Sheet flows emerge as flat, vast expanses of liquid rock. They spread rapidly across the ridge before finally solidifying. Sometimes, the molten interior drains away from a cooling sheet. This draining leaves behind hollow, fragile lava pillars and arches. Deeper below the basalt layer, different rock types slowly form. Magma that cools slowly underground transforms into solid gabbro. Gabbro features large, visible crystals of pyroxene and feldspar. These intrusive rocks provide structural stability to the lower crust. Even deeper, dense peridotite rocks represent the upper mantle layer. The geological architecture heavily influences local mineral compositions. Seawater slowly percolates downward through deep cracks in the basalt. The freezing water descends toward the shallow magma chamber. Intense subterranean heat warms the descending water to extreme temperatures. This superheated fluid undergoes complex chemical reactions with the rocks. The water strips valuable minerals from the surrounding hot basalt. Magnesium and sulfates drop out of the seawater entirely. Meanwhile, the fluid absorbs heavy metals from the volcanic crust. Iron, copper, and zinc dissolve completely into the hot liquid. Trace amounts of gold and silver also enter the solution. The mineral-rich fluid becomes highly buoyant and rises rapidly. It shoots back up through the crust toward the ocean floor. This fluid emerges from the seafloor at nearly 400 degrees. Upon hitting the cold ocean, the dissolved minerals instantly precipitate. Tiny particles of metal sulfide solidify in the dark water. These settling particles slowly build massive hydrothermal vent chimneys. The chimneys consist primarily of chalcopyrite, sphalerite, and pyrite minerals. Chalcopyrite provides a rich source of deep-sea copper deposits. Sphalerite contributes significant concentrations of zinc to the structures. Anhydrite forms the initial outer walls of these growing chimneys. Later, harder sulfide minerals replace the fragile anhydrite framework. This continuous mineral deposition creates the densest vent fields known. The oceanic crust at the exact ridge axis has zero age. It represents the youngest solid surface on our entire planet. As new lava erupts, it pushes older rock outward horizontally. The crust ages symmetrically as it moves away from the center. 10 kilometers away, the seafloor might be several 100,000 years old. 50 kilometers out, the basalt has existed for millions of years. Scientists measure this crustal age using paleomagnetic dating techniques. Earth's magnetic field periodically reverses its global polarity. Cooling lava locks in the ambient magnetic field direction permanently. This creates alternating stripes of magnetic polarity across the seafloor. Research vessels tow magnetometers to read these ancient magnetic records. The wide magnetic stripes confirm the extremely fast spreading rate. Older crust becomes colder, denser, and thicker over geological time. It slowly sinks deeper into the mantle as it travels outward. Sediment gradually covers the aging basalt far from the ridge axis. However, the central rise remains completely free of thick sediment. Only a light dusting of biological debris covers the youngest rocks. This pristine exposure allows geologists to study raw planetary formation. The continuous renewal erases older geological evidence at the axis. Every eruption resets the geological clock for that specific location. Scientists use sound waves to probe beneath the ocean floor. Seismic reflection profiles reveal the hidden architecture of the ridge. Air guns release acoustic pulses that travel through the deep water. These sound waves penetrate the basalt and bounce off internal boundaries. Hydrophone arrays trail behind research ships to catch the returning echoes. This acoustic data creates a detailed cross-section of the ocean crust. The images show the exact shape of the axial magma chamber. It appears as a thin, bright seismic reflector on the monitors. The liquid magma lens measures only a few dozen meters thick. However, it stretches for kilometers along the length of the ridge. Below this liquid lens lies a massive zone of crystal mush. This mush consists of partially solidified minerals and trapped liquid magma. The mush zone extends several kilometers down toward the upper mantle. It provides the steady thermal energy required for hydrothermal circulation. Geophysicists like Dr. John Orcutt pioneered these deep seismic imaging techniques. Their research proved the continuous nature of the magma supply here. Slower ridges have isolated, temporary magma chambers that eventually freeze solid. The East Pacific Rise maintains a permanent, active molten core. This continuous heat source drives the densest concentration of hydrothermal vents. The underlying geology directly controls the placement of every single chimney. Tectonic forces create distinct patterns of fractures across the seafloor. Extensional stress pulls the cooling basalt apart in parallel lines. Long, straight fissures develop parallel to the main ridge axis. Some of these gaping cracks stretch for thousands of meters. They can reach depths of several hundred meters into the rock. These open fissures provide perfect conduits for rising hydrothermal fluids. Normal faults also form as the crust stretches and thins out. Blocks of solid rock slip downward along these angled fault planes. This slipping creates small, step-like cliffs called fault scarps. Submersibles must carefully navigate around these jagged, vertical rock faces. The fault scarps expose older layers of pillow basalts to view. Geologists examine these exposed cliffs to study past volcanic eruption cycles. Thick layers of collapsed lava tubes appear in the cliff walls. The fractures also allow deep ocean water to penetrate the crust. This continuous water circulation cools the newly formed tectonic plates slowly. Without this cooling, the oceanic crust would melt completely. Advanced laboratories analyze the chemical signatures of the recovered basalts. Scientists study isotopic ratios of strontium and neodymium in the rocks. These isotopes reveal the deep mantle origins of the erupting magma. The East Pacific Rise basalts show a highly depleted chemical signature. This means the source mantle melted previously in ancient geological history. Incompatible elements left the mantle rock billions of years ago. The remaining mantle produces a very specific type of mid-ocean basalt. Geochemists refer to this common rock type as NMORB. Normal mid-ocean ridge basalt covers most of the global seafloor. Occasionally, isolated seamounts erupt slightly different lavas near the ridge axis. These off-axis volcanoes tap into deeper, more enriched mantle material. Researchers dredge rock samples from these seamounts using long steel cables. A heavy metal basket drags across the seafloor to collect rocks. The ship's winch slowly pulls the heavy geological samples to the surface. Back in the lab, mass spectrometers measure the exact elemental concentrations. Helium isotope ratios provide clues about gases trapped inside the Earth. Primordial helium-3 escapes from the mantle through the hydrothermal vents. Oceanographers track this rare helium plume as it drifts thousands of miles. The gas plume maps the invisible deep-sea currents across the Pacific. This complex chemistry fascinates modern deep-sea researchers. We descend again into the East Pacific Rise. The water pressure at this depth is incredibly immense. Our submersible hovers near the active hydrothermal vents. Darkness wraps around the titanium hull of Alvin. We observe the shimmering fluids rising from the crust. This deep environment holds a highly complex chemical signature. Superheated water mixes with the freezing abyssal ocean. The resulting chemical soup defies normal oceanic conditions. The East Pacific Rise features extreme chemical gradients. Every vent emits a unique blend of dissolved minerals. Scientists carefully collect samples using specialized titanium syringes. These syringes preserve the integrity of the deep fluids. We will explore the specific chemistry of this region. The local pH levels here are remarkably low. Normal seawater maintains a mildly alkaline pH of 8. Hydrothermal fluids emerge with a highly acidic nature. Measurements show pH values dropping as low as 3. This acidity resembles that of common household vinegar. Dr. Karen von Dam documented these extreme pH shifts. She analyzed samples from the 9 degrees north sector. The acidic fluid dissolves metals from the basaltic rock. This low pH environment prevents the precipitation of magnesium. Instead, the fluids carry massive amounts of dissolved iron. Instruments on ROV Jason continuously monitor these acidic plumes. The transition from acidic to alkaline happens very rapidly. Cold seawater quickly neutralizes the rising vent fluids. This rapid mixing creates microscopic zones of varying pH. Microbes thrive precisely within these steep chemical gradients. Salinity variations further define the East Pacific rise chemistry. Average ocean water contains roughly 35 practical salinity units. Vent fluids display dramatic deviations from this standard baseline. Subsea floor boiling causes a process called phase separation. Water separates into a dense brine and a light vapor. The vapor phase contains very low concentrations of salt. Some vents emit fluids with almost zero measurable salinity. Conversely, the remaining brine becomes extremely dense and salty. This heavy brine can pool beneath the ocean floor. Scientists recorded brines with double the salinity of seawater. Dr. Meg Tivy modeled these complex phase separation events. Her work explains the shifting salinity over several decades. Salinity dictates the buoyancy of the emerging hydrothermal plumes. Fresh vapor rises quickly toward the upper ocean layers. Dense brines linger near the base of the mineral chimneys. Hydrogen sulfide is the defining molecule of this ecosystem. This toxic gas smells like rotten eggs at the surface. In the deep ocean, it provides abundant chemical energy. Concentrations of hydrogen sulfide reach extraordinary levels here. Fluids contain up to 10 millimoles per kilogram. This concentration is lethal to most surface marine life. However, specialized bacteria oxidize this sulfide for cellular energy. Magma deep below the crust supplies the necessary sulfur. Seawater sulfate transforms into sulfide during high-temperature heating. This reduction process creates the energy-rich sulfide compounds. Chemical sensors detect sulfide plumes drifting miles away. The East Pacific rise produces more sulfide than other ridges. This abundance fuels the incredibly dense biological communities nearby. Dr. Nadine Labrise mapped these microscopic sulfide gradients. She deployed microelectrodes directly into the shimmering water. Her measurements revealed sharp drops in sulfide within millimeters. Methane gas also flows from the East Pacific rise. Unlike sulfide, methane production relies on different geological processes. Olivine minerals in the mantle react with heated water. This specific hydration reaction is known scientifically as serpentinization. Serpentinization naturally produces abundant amounts of hydrogen and methane gas. However, the East Pacific rise has relatively low methane. The fast-spreading ridge exposes very little deep mantle rock. Basalt dominates the crustal composition at this specific location. Therefore, methane concentrations remain below 1 millimole per kilogram. Scientists use gas chromatographs to measure these exact amounts. Isotope analysis reveals the purely abiotic origin of this methane. The gas simply bubbles up from the cooling magma chambers. Methane provides a secondary energy source for some microbes. These methanotrophic bacteria consume the gas as it escapes. Heavy metals constitute a major part of the fluid chemistry. Iron concentrations routinely exceed those of normal seawater. The superheated acidic water aggressively leaches iron from basalt. Zinc and copper also dissolve easily into the hot fluid. These metals remain completely dissolved under high pressure and heat. Upon contacting cold seawater, the dissolved metals suddenly precipitate. This rapid precipitation forms the iconic black smoker clouds. Iron sulfide particles create the dark coloration of the plumes. Copper-iron sulfide minerals build the physical chimney structures. These mineral deposits grow several centimeters every single day. The East Pacific Rise hosts massive sulfide mineral deposits. Geologists map these deposits to understand ancient ore formations. Dr. Robert Ballard first sampled these metallic chimneys. His team brought fragile mineral spires back to the surface. We must compare this region to the Mid-Atlantic Ridge. The Mid-Atlantic Ridge spreads at a much slower rate. This slow spreading allows deep mantle rocks to reach the seafloor. Consequently, Atlantic vents exhibit very different chemical profiles. Atlantic vents often have much higher concentrations of dissolved iron. The East Pacific Rise fluids are relatively depleted in iron. Instead, Pacific fluids contain higher levels of dissolved gases. Hydrogen sulfide dominates the Pacific vent chemical signatures. This difference directly impacts the local biological ecosystems. Pacific vents support giant tube worms that rely on sulfide. Atlantic vents host blind shrimp that tolerate heavy metals. The underlying geology dictates the entire chemical environment. Fast-spreading ridges produce consistent but short-lived vents. Slow-spreading ridges create massive, long-lasting hydrothermal fields. Another stark contrast exists with the Lost City hydrothermal field. Lost City sits far from the main volcanic ridge axis. Its chemistry relies entirely on the serpentinization of peridotite. The East Pacific Rise is driven by intense volcanic heat. Lost City fluids are relatively cool, reaching 90 degrees Celsius. Pacific black smokers routinely exceed 350 degrees. More importantly, Lost City fluids are extremely alkaline. Their pH levels can reach a highly basic value of 11. This is the exact opposite of the acidic Pacific vents. Lost City produces massive quantities of hydrogen and methane. The chimneys at Lost City are made of white calcium carbonate. Pacific chimneys consist of dark, heavy metallic sulfide minerals. These comparisons highlight the incredible diversity of ocean chemistry. The East Pacific Rise represents the classic volcanic vent model. Helium isotopes provide another fascinating chemical tracer here. Primordial helium-3 escapes from the Earth's deep mantle. This rare isotope was trapped during the planet's formation. Hydrothermal vents release this ancient gas into the modern ocean. The East Pacific Rise is a major source of helium-3. Oceanographers track this helium plume across the entire Pacific basin. The gas spreads westward for thousands of miles. Dr. John Lupton pioneered the study of these helium plumes. His research revealed the vast scale of hydrothermal circulation. Helium does not react with other chemicals in the water. It serves as a perfect marker for deep ocean currents. Sensors on autonomous underwater vehicles map these invisible gas trails. The deep currents carry the chemical signature through the dark. This slow movement creates a calming rhythm in the abyss. Dissolved silica plays a crucial role in chimney evolution. Hot vent fluids carry high concentrations of dissolved silicic acid. As the fluid cools, the silica begins to precipitate outward. Amorphous silica coats the exterior of the aging sulfide chimneys. This glassy coating effectively seals the porous mineral walls. The sealing process insulates the superheated fluids traveling inside. Silica precipitation also helps fossilize the surrounding microbial mats. Scientists find ancient microbes perfectly preserved in silica deposits. The East Pacific Rise features many of these mature, sealed chimneys. Their structural integrity depends on this delicate chemical balance. Without silica, the metallic spires would quickly crumble and collapse. The slow deposition of minerals mimics a patient geological clock. Chemical reactions also occur deep beneath the ocean floor. Cold seawater percolates downward through cracks in the crust. It travels miles deep before nearing the magma chamber. During this descent, the water loses all its dissolved oxygen. Magnesium drops out of the fluid, bonding with the rock. This process fundamentally alters the surrounding basaltic crust. The chemically modified water then heats up and rises rapidly. This subsea flow journey creates a hidden chemical reactor. Scientists believe a massive biosphere exists within these dark rocks. Microbes might live deep within the crustal fractures. They would survive entirely on the subsea floor chemical reactions. Dr. John Barros championed the idea of this deep biosphere. The chemistry of the East Pacific Rise supports his theories. Life here depends on chemistry rather than solar energy. The background seawater chemistry is equally important to this system. Deep Pacific waters contain remarkably low levels of dissolved oxygen. It originated in the freezing surface waters of the Antarctic. During its long journey, biological processes slowly consumed the oxygen. When this oxygen-poor water meets the vent fluids, reactions slow. The low oxygen environment prevents the rapid oxidation of sulfide. This allows the toxic gas to persist slightly longer. Microbes have more time to harvest the chemical energy. The sluggish deep ocean currents gently sweep the chemical plumes. The water temperature remains a constant 2 degrees Celsius. This freezing background perfectly contrasts the boiling vent emissions. The thermal and chemical gradients remain remarkably stable over time. This stability provides a reliable sanctuary for the deep ecosystem. Collecting these chemical samples requires extraordinary engineering and patience. The DSV Alvin uses specialized isobaric gas-tight samplers. These titanium cylinders capture fluids at exact seafloor pressures. Maintaining pressure prevents dissolved gases from bubbling away during ascent. Dr. Jeffrey Sewall designed these innovative deep-sea sampling devices. The robotic arms of Alvin carefully position the titanium inlet. They avoid drawing in the surrounding cold, freezing seawater. A successful sample captures the true essence of the crust. Back in the laboratory, gas chromatographs analyze the trapped molecules. Mass spectrometers weigh the individual isotopes of sulfur and carbon. These precise instruments reveal the invisible chemical architecture. Every dive adds another data point to the oceanographic map. The East Pacific Rise remains the most thoroughly sampled ridge. The continuous chemical cycles of the abyss are incredibly peaceful. Elements transition from solid rock to dissolved liquid seamlessly. Gases dissolve into the immense weight of the deep ocean. Minerals crystallize and fall gently back to the dark seafloor. There is a quiet, eternal rhythm to this chemical exchange. Magma supplies the heat, and seawater provides the medium. Chemistry translates this geological power into biological life. The East Pacific Rise perfects this silent, dark alchemy. We watch the shimmering fluids rise and slowly dissipate. The heavy metals sink, building silent monuments in the dark. The lighter gases drift away into the endless oceanic currents. This perfect chemical balance has persisted for millions of years. It will continue long after our submersible returns to the surface. The deep ocean keeps its chemical secrets well guarded. You can imagine the slow drifting of the invisible molecules. The gentle mixing of hot and cold creates a soothing flow. Let your mind sink into the steady rhythm of the vents. The darkness of the East Pacific Rise is deeply comforting. The immense pressure holds everything in a state of calm. The chemical gradients blend smoothly into the vast, quiet ocean. Every dissolved mineral finds its resting place in the abyss. The heavy iron particles drift slowly down to the seabed. The deep currents carry the faint echoes of the earth. Rest in the silent, enduring chemistry of the deep ocean. The East Pacific Rise supports incredibly dense biological communities. These hydrothermal vents host life found nowhere else globally. Biomass here rivals the most lush tropical rainforests perfectly. Organisms thrive at crushing depths of 2,500 meters. Total darkness blankets this vibrant underwater ecosystem completely forever. Ambient water temperatures hover constantly around 2 degrees Celsius. Yet boiling fluids emerge nearby at 350 degrees Celsius. This sharp thermal gradient creates unique biological niches everywhere. Populations cluster tightly around the active mineral chimneys constantly. Scientists first observed this oasis in February of 1977. Geologist John Corliss peered through the Alvin submersible window. He expected to see barren basaltic lava formations below. Instead, a dense field of strange animals appeared suddenly. The submersible hovered gently above the Galapagos Rift segment. Coordinates marked the location exactly at 0 degrees longitude. Massive white clams rested silently on the dark rocks. These bivalves measured up to 30 centimeters in length. Researchers later named this giant clam species Calyptargina magnifica. Their thick shells protect them from the harsh environment. Blood-red tissue fills the interior of these massive mollusks. The red coloration comes from human-like hemoglobin protein molecules. This specialized blood binds hydrogen sulfide from the vents. Giant clams lack a functional digestive tract completely today. They rely entirely on internal symbiotic bacteria for nourishment. These microbes convert toxic chemicals into usable organic carbon. Dense clusters of clams wedge themselves into basalt crevices. Nearby, vent mussels form expansive beds across the seafloor. Bathymodialus thermophilus is the dominant mussel species found here. They attach to bare rock using strong byssal threads. Mussel population densities often exceed 1,000 per square meter. The most striking resident is the giant tube worm. Marine biologists named this remarkable organism Riftia pachyptela officially. These worms grow inside tough, white chitinous protective tubes. Some tubes reach towering heights of nearly 3 meters. They grow incredibly fast in the warm vent fluids. Growth rates can exceed 80 centimeters in a single year. Their stark white tubes contrast beautifully with the darkness. A brilliant red plume extends from the tube apex. This delicate structure acts as a highly efficient gill. It absorbs oxygen, carbon dioxide, and hydrogen sulfide simultaneously. The worm retracts its plume instantly when threatened nearby. Blind vent crabs frequently attempt to nip these plumes. Inside the worm lies a specialized organ called the trophosome. This dark tissue makes up half the worm's weight. Billions of symbiotic bacteria pack tightly into this organ. Colleen Cavanaugh first identified this revolutionary biological relationship locally. Her 1981 research changed our understanding of deep-sea life. The bacteria perform chemosynthesis without any solar energy present. They oxidize sulfur compounds to produce vital cellular energy. This process sustains the massive tube worm communities entirely. Another extraordinary endemic species is the famous Pompeii worm. French researchers discovered Alvanella pompeiana in the early 1980s. These worms inhabit the hottest zones of the chimneys. They build papery tubes directly on the active smokers. Their tails rest in water exceeding 80 degrees Celsius. Meanwhile, their heads experience cooler 20-degree ocean water currents. This represents the highest thermal gradient for any animal. A thick fleece of bacteria covers their pale backs. These microbes secrete special proteins to insulate the worm. They also detoxify heavy metals erupting from the vent. Scavengers constantly patrol the dense tube worm thickets quietly. The dominant predator here is the blind vent crab. Taxonomists designated this unique crustacean species as Bythagria thermodron. These white crabs lack functional eyes in their adulthood. However, their larval stages possess fully developed visual organs. They navigate the dark landscape using highly sensitive antennae. Vent crabs tear pieces of flesh from exposed worms. They also graze heavily on the surrounding microbial mats. High pressure prevents their blood from boiling near vents. Their population density reaches dozens per square meter locally. Gallet-eyed squat lobsters also inhabit the East Pacific Rise. Munidopsis polymorpha scurries across the hardened basaltic lava flows. These pale crustaceans remain slightly further from the heat. They prefer the cooler periphery of the hydrothermal field. Swarm behavior is common among these deep-sea biological scavengers. Amphipods flit rapidly through the warm, shimmering water column. These tiny crustaceans provide food for larger vent predators. Pink vent fish swim lazily among the towering chimneys. Thermasis cerberus lacks scales and possesses a gelatinous body. These slow-moving fish hunt amphipods and small marine worms. Microbial mats form the foundational base of this ecosystem. Vast carpets of bacteria cover the surrounding rocky seafloor. Veggiatoa filaments create thick white patches on the basalt. These mats resemble freshly fallen snow in the darkness. They thrive where warm vent fluid meets cold sea water. Some bacterial mats reach several centimeters in total thickness. They consist of billions of individual single-celled organisms clustered. These microbes utilize hydrogen sulfide as their energy source. Microbiologist Holger Janisch studied these specific bacterial strains extensively. His work proved chemosynthesis drives the entire vent food web. Thiomargarita bacteria also appear in these dense microbial communities. They store massive sulfur granules inside their cellular vacuoles. These granules glitter faintly under the submersible lighting systems. Archaea dominate the hottest fluids emerging from the chimneys. Methanoporous candleri survives water temperatures up to 122 degrees Celsius. These hyperthermophiles reproduce rapidly in the boiling mineral water. They represent some of the oldest living life forms on Earth. Their genetic code offers clues about early biological evolution. Scientists collect them using specialized titanium water sampling bottles. Laboratory cultivation of these microbes requires extreme pressurization chambers. The total biomass here astounds visiting marine biologists constantly. Estimates suggest 20 to 30 kilograms per square meter. This biological density contrasts sharply with the surrounding abyss. Most of the deep ocean floor is an empty desert. Standard deep-sea biomass is just milligrams per square meter. The East Pacific rise concentrates life into narrow bands. These thriving vent communities span only a few dozen meters. Beyond the chemical influence, the rich life abruptly stops. Starfish and sea cucumbers roam the barren outer edges. They wait patiently for organic debris to drift outward. Hydrothermal vent biological communities undergo rapid ecological succession phases. Volcanic eruptions frequently pave the seafloor with fresh lava. This molten rock destroys the existing biological communities instantly. However, new cracks quickly release fresh hydrogen sulfide fluids. Microbial mats are the first pioneering organisms to colonize anew. They form a sticky biofilm over the glassy basalt. Tevnia jericonana is a smaller tube worm pioneer species. These fragile worms settle on the newly formed mats. They tolerate the highly toxic initial vent fluid chemistry. Within a year, they establish a thriving young colony. Eventually, the giant Rifsha pachyptila worms arrive and dominate. They outcompete the smaller Tevnia worms for vital resources. The giant worms grow over the initial pioneer species. This transition marks the shift toward a climax community. Mussels and giant clams settle into the cooling periphery. They require lower hydrogen sulfide concentrations to survive comfortably. The entire ecological succession takes less than 5 years. This rapid growth is unparalleled in deep ocean environments. Most deep-sea organisms grow at incredibly slow, measured rates. Vent creatures live brief, highly accelerated biological lifespans instead. Over 90% of vent species are entirely endemic. They exist nowhere else in the vast global ocean. The East Pacific rise acts as a biological highway. Ocean currents transport microscopic larvae along the ridge axis. These tiny larvae must find an active vent to survive. Most perish in the freezing, nutrient-poor abyssal water column. Successful settlement requires precise thermal and chemical environmental cues. Genetic studies reveal strong connections between distant vent fields. Populations separated by thousands of kilometers share identical DNA. This proves larvae travel vast distances along the ridge. The submersible Alvin continues to sample these dense communities. Robotic vehicles like Jason provide continuous high-definition video feeds. Scientists use precise manipulator arms to collect fragile specimens. They place the organisms into insulated bioboxes for transport. These special containers maintain the extreme cold of the deep. Without insulation, the animals would degrade during the ascent. Researchers also deploy time-lapse cameras near the tube worms. These instruments record the daily rhythms of vent life. Observations show crabs feeding actively during tidal pressure changes. Even at this depth, lunar cycles subtly influence behavior. Pale anemones cling tightly to the dead mineral chimneys. They use stinging tentacles to capture passing microscopic larvae. Small limpets graze continuously on the exposed basaltic rocks. Deep-sea octopuses occasionally visit the East Pacific rise vents. Volcanoctopus hydrothermalis is a rare, ghostly white cephalopod species. These intelligent predators lack ink sacs completely in darkness. They hunt blind crabs among the dense worm tubes. The octopuses move with slow, deliberate grace underwater constantly. Their presence adds complexity to the vent food web. Every creature here adapts perfectly to this extreme environment. Early explorers noticed strange yellow spheres floating near vents. Researchers nicknamed these delicate structures as deep-sea dandelions originally. These organisms are actually complex colonies called benthic siphonophores. Thermopaleotaroxaca anchors itself to rocks using thin tentacles. They scavenge dead organic matter drifting from the chimneys. The dandelions fall apart easily when brought to the surface. Only careful chemical fixation preserves their fragile gelatinous bodies. Their presence often indicates a dying hydrothermal vent system. They thrive when fluid flow begins to slow down. This signals the inevitable end of the local ecosystem. Delicate serpulid worms also attach to the basaltic rocks. They filter microscopic particles from the surrounding ocean water. Their feathery crowns retract quickly at the slightest disturbance. Thousands of brittle stars carpet the outer vent periphery. Archaeoroids extend their long, spiny arms into the current. They capture marine snow falling from the upper ocean. These echinoderms form a living boundary around the oasis. Their bodies overlap to create dense, writhing biological mats. Scientists often struggle to see the underlying rock formations. The sheer volume of living tissue obscures the geology. The East Pacific rise continues to yield new discoveries. Marine biologists plan future expeditions to this remote location. Advanced sensors will monitor the chemical fluctuations more precisely. We still understand very little about deep-sea larval dispersal. New genetic sequencing techniques will map these hidden populations. The harsh environment requires constant technological innovation from engineers. Every dive reveals another secret of this dark world. These alien ecosystems expand our definition of habitable environments. They hint at possible life on distant ocean moons. The dense creature community sleeps silently in the abyss. Our journey through this biological hotspot slowly concludes tonight. The giant tube worms sway gently in the warm currents. Blind crabs rest quietly among the towering mineral spires. Microbial mats continue their silent work in the dark. The hydrothermal fluids flow steadily from the Earth's crust. Life persists here against all expected biological odds beautifully. This deep-sea sanctuary remains isolated from the surface world. The immense pressure embraces the ecosystem in a calm hold. We leave these extraordinary creatures to their eternal night. The deep ocean keeps its secrets safe and undisturbed. The East Pacific rise holds a rare biological sanctuary. This ecosystem thrives in absolute darkness at deep coordinates. Sunlight never reaches these profound benthic geological formations. Life here depends entirely on chemical energy from below. Scientists identify this unique biological process as chemosynthesis. Hydrogen sulfide replaces sunlight as the primary energy source. The biological density here surpasses all other oceanic ridges. Researchers first discovered this alien world in 1977. Geologists aboard the submersible Alvin made this historic observation. They found thriving communities near 9 degrees north latitude. No one expected such abundant life at these extreme depths. The surrounding ocean floor is mostly a barren dark desert. Yet the hydrothermal vents support a lush biological oasis. Biomass concentrations here rival tropical surface coral reef systems. Microscopic organisms form the foundation of this unique food web. Thermophilic bacteria process toxic chemicals pouring from the crust. These microbes withstand temperatures exceeding 100 degrees Celsius. They oxidize hydrogen sulfide to create complex organic carbon. This chemical conversion sustains every living creature down here. Some bacteria drift freely within the warm fluid plumes. Others form thick microbial mats across the jagged basaltic rocks. These white mats look like fresh snow falling underwater. Marine biologist Holger Janisch studied these deep vent microbes. He proved that chemosynthesis could support massive animal populations. Before his work, science believed only sunlight sustained life. The East Pacific rise completely rewrote biological textbook paradigms. Energy flows upward from the Earth instead of downward. Geothermal energy provides a constant and highly reliable food source. Giant tube worms dominate the East Pacific rise vent fields. Scientists officially classify this iconic species as Rifsha pachyptela. These incredible worms grow up to 3 meters in length. They possess no mouth, no gut, and no digestive stomach. Instead, they rely entirely on internal symbiotic bacteria populations. A specialized internal organ called the traphosome houses these microbes. Blood vessels transport hydrogen sulfide directly to this organ. The worm absorbs oxygen from the surrounding cold seawater. Hemoglobin gives the tube worm plumes their vibrant red coloration. This complex hemoglobin binds both oxygen and toxic sulfide molecules. The bacteria consume these compounds and produce cellular nourishment. This perfect symbiosis allows tube worms to grow incredibly fast. Biologist Craig Carey measured their growth at remarkable rates. They can grow nearly 1 entire meter in a single year. This represents the fastest growth rate of any marine invertebrate. Bathymodialus mussels also colonize the cracked basaltic seafloor environment. These deep-sea bivalves attach themselves using strong byssal threads. They settle in cooler transition zones around the active vents. Water temperatures here average around 10 to 15 degrees Celsius. Like tube worms, these mussels harbor specialized chemosynthetic bacteria gills. However, mussels retain a functional digestive system for filter feeding. They can consume free-floating microbes from the dark water column. This dual feeding strategy ensures their survival during environmental changes. Giant white clams called Calyptargina magnifica share this specific habitat. These clams wedge themselves deeply into the rocky basaltic fissures. Their specialized foot absorbs sulfide directly from the geological cracks. A thick white calcium shell protects them from crushing pressures. The ambient pressure here measures 250 atmospheres. These vast bivalve beds create complex structural habitats for others. Swarms of small crustaceans navigate through the dense tubeworm clusters. Squat lobsters scavenge continuously across the warm rocky surfaces. Their pale white bodies contrast sharply against the dark basalt. Scientists identify them primarily as species of the genus Munidopsis. These bottom scavengers feed on bacterial mats and fallen debris. Pythogorid crabs act as active predators in this benthic zone. They use heavy front claws to crush small vent snails. These crabs also graze directly on the delicate tubeworm plumes. When threatened, the tubeworms quickly retract into their protective tubes. Albino-carried shrimp swim gracefully through the shimmering warm vent fluids. Unlike their Atlantic cousins, these Pacific shrimp retain functional eyesight. They do not form massive swarms around the smoking chimneys. Instead, they carefully pick food from the biological surface layers. Energy transfers efficiently from the microbes to these roaming crustaceans. Apex predators silently patrol the dark outer edges of vents. The vent eelpout fish is a common deep-sea visual sight. Zooarcid fish weave slowly through the dense mussel bed formations. They hunt for small amphipods and vulnerable juvenile vent crabs. These fish possess a natural biological resistance to high toxicity. Hydrogen sulfide levels here would kill most surface marine life. Yet the vent fish thrive seamlessly in this chemical soup. Vulcanoctopus hydrothermalis represents a highly specialized cephalopod benthic predator. This small ghost white octopus crawls slowly over the jagged rocks. It has no ink sac because ink remains useless in darkness. The octopus relies heavily on tactile sensors to find hidden prey. It probes the dark crevices for resting squat lobster targets. These stealthy predators maintain the delicate balance of the ecosystem. They prevent any single species from dominating the available resources. The East Pacific rise differs greatly from Atlantic ridge systems. The Mid-Atlantic ridge features deep and slow-spreading rift valleys. Atlantic vents are heavily dominated by swarms of blind shrimp. Tubeworms are completely absent from those distant Atlantic vent fields. Scientists attribute this to vastly different geological crust spreading rates. The East Pacific rise spreads at a very rapid tectonic pace. This creates frequent volcanic eruptions and massive habitat destruction events. Pacific vent species must grow and reproduce at extreme speeds. Atlantic vents remain geologically stable for many thousands of years. Therefore, Atlantic species evolved slower and longer-lasting life cycles. The Pacific tubeworms are ultimate pioneer species of the deep. They quickly colonize newly formed lava flows after violent eruptions. This rapid turnover creates a dynamic and changing biological landscape. Researchers use the ROV JSON to monitor these ecosystem shifts. A vent ecosystem undergoes a predictable sequence of biological succession. A new volcanic eruption wipes out existing biological community structures. Fresh lava cools rapidly into sterile and glassy rock formations. Within a few weeks, warm mineral fluids begin seeping upward. Microbial mats are always the very first organisms to arrive. They form a thick white biological coating over the rocks. Small Tevnia jericonana tubeworms settle next on the fresh basalt. These smaller worms tolerate highly toxic and newly formed vents. Slowly, the fluid chemistry changes as the hydrothermal vent matures. The giant riftsha tubeworms eventually replace the smaller pioneer species. Mussels and clams arrive much later as the temperatures drop. This entire ecological succession process can happen within 5 years. Oceanographer Richard Lutz documented this rapid biological recovery timeline perfectly. Such ecological speed is entirely unique to the East Pacific rise. Chemosynthetic ecosystems demonstrate remarkable energy conversion efficiency rates down here. Surface ecosystems lose massive energy between each consecutive trophic level. Sunlight must pass through phytoplankton, zooplankton, and small schooling fish. Deep-sea vent symbiosis eliminates many of these wasteful intermediate steps. The tubeworms grow massive by directly utilizing internal bacterial energy. This direct energy transfer supports an incredibly high local biomass. Scientists estimate biomass here reaches tens of kilograms per square meter. This density rivals the most productive surface ocean biological environments. Yet this oasis exists surrounded by absolute deep biological starvation. The abyssal plain nearby supports very few living benthic creatures. Food falls from the surface are extremely rare and unpredictable. The vent provides a continuous and reliable stream of chemical energy. This creates a highly isolated island of life in the abyss. In 1991, a major eruption occurred at 9 degrees north. Scientists arrived shortly after the violent volcanic activity had ceased. They witnessed the immediate aftermath of a massive seafloor eruption. Dead tubeworms were scattered across the freshly cooled lava flows. This event provided a unique opportunity to study biological colonization. Biologists deployed time-lapse cameras to carefully watch the ecosystem recovery. They observed microscopic larvae drifting in the deep ocean currents. These larvae somehow locate the invisible chemical vent fluid plumes. The exact navigation mechanism remains a profound deep scientific mystery. Perhaps they sense minute temperature changes in the surrounding water. Maybe they detect faint traces of dissolved hydrogen sulfide molecules. Once they find a suitable vent, they drop to the seafloor. They must establish their bacterial symbiosis almost immediately to survive. Deep ocean currents act as massive highways for vent larvae. The East Pacific rise features strong and complex bottom currents. These currents sweep along the massive underwater volcanic mountain range. They carry biological genetic material between distant hydrothermal vent fields. Biologist Robert Vrijgenheek studied the complex genetics of vent species. He found remarkable genetic similarities across vast Pacific oceanic distances. This proves that isolated vent communities are deeply and genetically interconnected. Larvae might travel hundreds of kilometers before finally settling down. They drift in a state of suspended biological cellular animation. The cold deep water slows their metabolic rates very significantly. Water temperatures away from the vents hover near 2 degrees Celsius. This extreme cold preserves the larvae for their long dark journey. When they encounter warm vent water, they awaken and settle. Vent ecosystems share biological similarities with other deep-sea benthic habitats. Cold seeps also rely entirely on chemical energy from the crust. Methane gas bubbles up from deep sediments at these cold seeps. Similar tubeworms and mussels thrive in those distant methane environments. However, cold seeps lack the extreme temperatures of active hydrothermal vents. Whale falls provide another temporary biological oasis in the deep ocean. A sunken whale carcass releases valuable sulfides as it slowly decays. Some vent species use these massive carcasses as biological stepping stones. They travel from one whale bone to another over multiple generations. Eventually, they may reach a newly active volcanic hydrothermal vent field. The East Pacific Rise serves as the ultimate biological destination. Its high density of vents ensures a constant warm habitat availability. The ecosystem relies on this vast interconnected network of chemical oases. Surviving the East Pacific Rise requires extreme physiological biological adaptations. Heavy metals continually pour from the towering black smoker chimneys. Copper, zinc, and lead saturate the surrounding deep seawater environment. These concentrations are highly toxic to normal shallow marine biology. Vent organisms have evolved special proteins to bind heavy metallic elements. Metallothioneins trap the toxic elements safely within their deep cellular tissues. This prevents heavy metal poisoning in the delicate internal biological organs. The extreme pressure also alters how cellular membranes must physically function. Deep-sea creatures incorporate special lipids to keep their cellular membranes flexible. Without these lipids, their cells would freeze under extreme hydrostatic pressure. Every biological mechanism here is perfectly tuned to the extreme environment. Scientists constantly study these unique proteins for potential future medical applications. Nature has solved complex biochemical problems in the dark ocean abyss. The beauty of this ecosystem lies in its ephemeral nature. A thriving vent community can suddenly die without prior warning. Geological shifts deep underground can block the hydrothermal plumbing system. The East Pacific Rise holds countless scientific mysteries. For decades, researchers have traveled to this remote boundary. Early expeditions relied on simple sonar surface mapping. Scientists could only guess at the abyssal landscape below. Everything changed during the late 20th century expeditions. Oceanographers wanted to see the volcanic ridge directly. They needed specialized vessels to breach the crushing depths. The pressure at 2,500 meters is immense. Standard submarines would instantly collapse under such weight. Engineers designed spherical titanium cabins to protect the crew. The human-occupied vehicle Alvin led the charge. This small submersible transformed deep ocean exploration forever. In 1979, a famous mission began. Researchers targeted a specific coordinate at 21 degrees north. They sought the source of strange temperature anomalies. Surface ships had detected warm water plumes earlier. Alvin descended slowly through the dark water column. It took 2 hours to reach the ocean floor. Outside the viewport, the water was pitch black. The pilots turned on the exterior halogen lights. Geologist Robert Ballard stared through the thick acrylic window. He expected to see barren basaltic lava flows. Instead, a towering mineral chimney emerged from the gloom. Dark, billowing fluid poured from the rocky summit. This was the first discovery of a black smoker. The expedition team was completely stunned by the sight. They carefully maneuvered Alvin closer to the venting fluid. A mechanical arm reached out with a temperature probe. The reading spiked to 350 degrees Celsius. The plastic housing on the probe actually began to melt. Scientists quickly realized the magnitude of this finding. Tjeerd van Andel documented the massive sulfide deposits. He mapped the mineral structures using simple grid systems. The surrounding ecosystem was thriving without any sunlight. biologist Holger Janusz studied the strange bacterial mats. He proved that chemosynthesis powered this deep-sea world. Microbes were converting hydrogen sulfide into organic energy. This revelation forced a rewrite of biology textbooks. Life could exist independently of the distant sun. The East Pacific Rise became a global scientific focal point. Subsequent expeditions brought more advanced technology to the ridge. The research vessel Nor served as a floating laboratory. Scientists worked around the clock analyzing water samples. They needed to understand the exact chemical composition. Titanium syringe samplers were developed for this specific task. These metal tubes maintained the extreme abyssal pressure. Fluid was brought to the surface without losing dissolved gases. Chemists carefully extracted the deep ancient hydrothermal fluids. They measured high concentrations of iron and manganese. Isotope analysis revealed the subterranean journey of the seawater. In the 1990s, exploration shifted to new coordinates. 9 degrees 50 minutes north became the primary target. This section of the ridge is incredibly active volcanically. Researchers established a long-term monitoring site here. They wanted to observe changes over many years. Oceanographer Cindy Lee Vandover piloted several crucial dives. She was the first female pilot of the Alvin submersible. Her work focused on the visual systems of blind shrimp. She documented how these creatures navigate the thermal gradients. They detect faint infrared radiation emitted by the vents. The introduction of remotely operated vehicles changed the methodology. ROV Jason allowed for continuous observation without human risk. A long fiber optic cable tethered Jason to the ship. High-definition video streamed live to the surface control room. Scientists could watch the seaflow on large digital monitors. They directed the robotic arms with precise joystick movements. Jason could stay submerged for days at a time. This endurance was impossible for human-occupied submersibles. Researchers meticulously mapped the biological communities along the fissure. They placed physical markers near specific tubeworm colonies. Autonomous underwater vehicles soon joined the scientific fleet. The Autonomous Benthic Explorer, known as ABE, mapped the terrain. ABE flew 50 meters above the rugged volcanic seafloor. It used multibeam sonar to create high-resolution bathymetric charts. These maps revealed intricate fault lines and collapse pits. Scientists used the data to locate hidden hydrothermal fields. ABE operated entirely on pre-programmed acoustic navigation grids. It glided silently through the dark ocean currents. Magnetic sensors recorded the polarity of the cooling basalt. This helped geologists calculate the spreading rate of the plates. In 1991, a major volcanic event occurred. Researchers arrived just after a massive seafloor eruption. Fresh lava had completely paved over the old event sites. The water was cloudy with white bacterial flocculant. Scientists named this phenomenon a deep ocean snowstorm. They deployed time-lapse cameras to watch the recovery. The biological succession happened much faster than anyone expected. Within months, new tubeworms settled on the fresh basalt. This proved the incredible resilience of hydrothermal ecosystems. The East Pacific Rise was a dynamic, ever-changing environment. Another massive eruption struck the exact same area in 2005. Scientists had instruments already deployed on the ocean floor. Many seismometers were tragically buried under molten rock. However, the surviving data provided unprecedented geological insights. Micro-earthquakes had steadily increased before the magma breached. This allowed researchers to build predictive volcanic models. They realized the ridge operates on a cyclic eruption schedule. Long-term observation was clearly essential for understanding the system. The Ocean Observatory's initiative was born from this realization. It aimed to establish permanent, cabled scientific infrastructure. Deploying permanent sensors at 2,500 meters is difficult. The corrosive seawater quickly degrades exposed metal components. Engineers utilized specialized titanium alloys and thick synthetic resins. They placed heavy sensor nodes directly on the ocean floor. Acoustic modems transmit the data through the water column. Surface buoys catch the sound waves and relay them via satellite. Scientists in mainland laboratories receive real-time telemetry. They can monitor bottom water temperatures from their desks. Geochemist Meg Tivy used this data to study chimney growth. She discovered that mineral structures can grow several centimeters daily. Deep-sea mass spectrometers were eventually brought to the ridge. These complex machines analyze dissolved gases in situ. They operate perfectly under 250 atmospheres of pressure. A delicate membrane separates the vacuum chamber from the ocean. The device measures exact concentrations of methane and carbon dioxide. This eliminates the need to bring unstable samples to the surface. Chemical reactions are observed exactly as they happen in nature. The accuracy of deep ocean chemistry improved dramatically. Researchers could map the chemical halos surrounding each vent. These invisible boundaries dictate where specific organisms can survive. The research vessel Atlantis frequently visits the East Pacific Rise. It carries the latest iteration of the Alvin submersible. Upgrades have given the vehicle a wider field of view. 5 overlapping cameras capture panoramic footage of the seafloor. Powerful LED arrays illuminate the dark volcanic landscape. The light reaches much further than the old halogen bulbs. Scientists can see the intricate textures of the pillow lavas. They use laser scaling tools to measure precise biological dimensions. 2 green laser dots project exactly 10 centimeters apart. This provides a perfect reference scale for the video recordings. Biologists deploy specialized colonization blocks near the active vents. These are simple squares of basalt or textured plastic. They provide an artificial substrate for deep-sea larvae. Researchers leave the blocks in place for an entire year. Upon retrieval, they catalog every microscopic organism attached. This reveals the complex sequence of ecological succession. Certain bacteria always arrive first to condition the surface. Small limpets and polychaete worms follow shortly after. Finally, the giant riftsha tube worms establish their dense clusters. The entire process is a delicate biological ballet. Geophysicists also study the deep crustal structure of the ridge. They use ocean bottom seismometers to listen to the Earth. These devices record the faint rumblings of moving magma. The sensors are dropped freely from the surface ship. They sink for hours before settling in the abyssal mud. A heavy iron anchor keeps them perfectly stationary. After a year, an acoustic command triggers a release mechanism. The sensor floats back to the surface for data extraction. This acoustic network reveals the shape of the subterranean magma chamber. It sits only a few kilometers beneath the hydrothermal vents. The Sentry autonomous underwater vehicle represents the next generation. Its unique shape allows for incredible vertical maneuverability. Sentry can dive deep into narrow volcanic fissures. It carries advanced chemical sensors to sniff out hydrothermal plumes. The vehicle follows the chemical gradient directly to the source. It essentially hunts for new black smokers automatically. During one expedition, Sentry mapped 50 square kilometers of ridge. It discovered dozens of previously unknown venting structures. The sheer density of thermal activity here is astonishing. No other mid-ocean ridge possesses such concentrated energy. Ocean drilling programs have also targeted the East Pacific Rise. The drill ship Joyd's Resolution positioned itself over the crust. It lowered a massive drill string through 2 kilometers of water. The diamond bit ground slowly into the hard basaltic rock. Extracting core samples from a spreading center is complex. The fractured rock tends to jam the drilling machinery. The retrieved cylinders of stone are scientific treasures. They show how seawater penetrates the crust and alters the minerals. Veins of green chlorite run through the cores. These altered rocks are the foundation of the hydrothermal system. Microbiologists study the deep biosphere hidden within these rocks. They crush the basalt samples in sterile laboratory environments. DNA sequencing reveals a hidden world of subterranean microbes. These organisms live inside tiny pores of the crust. They survive on the chemical energy of the cooling rock. This subsurface biosphere might contain immense amounts of carbon. The East Pacific Rise is a window into this hidden realm. Every expedition uncovers another layer of biological complexity. Scientists share this data through open-access databases. Global collaboration is essential for understanding the deep ocean. In recent years, biological sampling has become much more refined. Suction samplers vacuum fragile organisms into rotating acrylic jars. This prevents damage to delicate deep-sea jellyfish. Scientists preserve the specimens in cold, pressurized containers. They study the unique enzymes that function at such high temperatures. Some of these proteins have revolutionized medical technology. Enzymes from vent bacteria are used in genetic testing. The deep sea holds countless undiscovered biochemical resources. Researchers respect the fragility of this extreme environment. They take only what is absolutely necessary for their studies. The future of East Pacific Rise exploration is automated. Seafloor observatories will stream continuous data for decades. Artificial intelligence will analyze massive archives of acoustic recordings. Algorithms can identify the sounds of impending eruptions. Gliders will patrol the water column above the ridge. They measure how the hydrothermal plumes influence ocean currents. These mineral-rich waters eventually affect global climate patterns. The deep ocean is intimately connected to the surface world. Every temperature fluctuation at the bottom ripples upward. The scientific watch over the abyss never truly ends. The East Pacific Rise stretches endlessly across the dark abyssal ocean floor. It differs greatly from the incredibly slow and ancient Mid-Atlantic Ridge. Here, the tectonic plates separate at 15 centimeters every single passing year. This rapid spreading creates the densest hydrothermal vent network on the planet. Marine scientists constantly compare this specific region to other ocean ridge systems. The Mid-Atlantic vents sit much deeper in the freezing dark ocean waters. Atlantic vents often reach crushing depths of nearly 4,000 meters down. Pacific vents mostly cluster around 2,500 meters deep in the dark. This shallower depth fundamentally changes the boiling point of the surrounding water. Pacific fluids exit the fractured crust at nearly 400 degrees Celsius. Atlantic fluids boil at higher extreme temperatures under immense water pressure. The Indian Ocean ridges show completely different mineral compositions and structural formations. East Pacific vents produce massive towering structures of dark black sulfide minerals. These Pacific structures grow much faster than the slow-forming Atlantic chimneys. A healthy Pacific chimney can easily grow several meters in 1 year. Atlantic chimneys might take decades to reach similar towering heights and widths. The biological communities also vary drastically across these global ocean ridge systems. Giant red tube worms completely dominate the East Pacific rise vent ecosystems. Atlantic vents are mostly covered by thousands of pale blind swarming shrimp. Indian Ocean vents feature strange scalefoot snails instead of the giant worms. This incredible biological diversity fascinates marine researchers all around the entire world. Each ridge system acts like an isolated underwater evolutionary laboratory for life. Ocean currents rarely carry fragile microscopic larvae between these distant ridge systems. This vast geographical isolation creates highly unique species at every major field. The East Pacific remains the most crowded hydrothermal neighborhood known to science. Research vessel Atlantis frequently visits this exact Pacific vent location for study. Scientists drop acoustic transponders to map the jagged volcanic seafloor below them. These transponders help navigate the dark waters with extreme and careful precision. Comparing global vents helps us understand planetary heat distribution perfectly and clearly. The Earth releases tremendous internal energy through these specific tectonic oceanic seams. The vast Pacific Ocean accounts for most of this natural thermal release. This heat transfer directly influences deep ocean current circulation patterns very strongly. These warmed currents slowly travel across the entire muddy global ocean floor. They gently mix vital minerals and nutrients into the barren abyssal plains. The East Pacific rise might hold vital clues to our biological origins. Many scientists believe cellular life began in these dark ancient thermal vents. The extreme heat provides endless chemical energy for basic early biological reactions. Early Earth possessed thousands of similar highly active underwater volcanic ridge systems. The ancient primordial oceans were highly toxic and completely devoid of oxygen. Hydrothermal fluids mix with cold seawater to create steep chemical energy gradients. These tiny natural gradients act exactly like microscopic biological power supply batteries. They slowly power the natural formation of complex organic carbon-based molecules. Researcher John Corliss first proposed this fascinating deep vent origin of life. He visited the nearby Galapagos Rift during the late 1970s expeditions. He quickly realized the bright sun was not absolutely necessary for life. Chemical synthesis could easily replace basic solar photosynthesis down in the dark. Deep-sea minerals act as vital natural catalysts for these chemical reactions. Iron and sulfur combine to form tiny protective microscopic mineral pocket structures. These microscopic pockets might have sheltered the very first fragile biological cells. Primitive RNA molecules could assemble safely within these warm protective rocky pores. The steady temperature gradients drive the rapid replication of these early molecules. This process closely mimics modern biological cellular respiration energy cycles very well. The last universal common ancestor likely lived happily in this extreme heat. Biologists call this ancient theoretical organism by the simple acronym named LUCA. Modern genetic studies link our oldest ancestors to these specific thermal environments. Thermophilic ancient bacteria still thrive in the East Pacific rise waters today. Their DNA remains remarkably similar to those ancient primitive organisms from before. This deep vent research extends far beyond our own pale blue planet. Astrobiologists study these vents to understand distant frozen alien worlds in space. Jupiter has a fascinating ice-covered moon known simply to astronomers as Europa. Europa hides a massive dark liquid ocean beneath its thick frozen crust. Saturn features a very similar icy moon called Enceladus in its orbit. Both moons likely harbor active hydrothermal vents on their deep alien seafloors. The East Pacific rise serves as an accessible extraterrestrial analog for scientists. If life survives here, it might easily survive in deep outer space. Exploring these vents requires incredibly advanced marine robotic technology and engineering systems. The physical and chemical challenges of the deep sea are truly immense. Water pressure at this depth easily crushes normal scientific recording equipment flat. The pressure greatly exceeds 250 standard atmospheric pressure units. Every square inch bears thousands of pounds of heavy freezing ocean water. Engineers build submarine passenger spheres from thick solid titanium metal alloy forgings. The famous submersible Alvin frequently visits the East Pacific rise for research. Alvin carries 3 brave people down into the absolute freezing pitch darkness. The gentle slow descent takes nearly 2 hours of quiet peaceful sinking. Outside the titanium sphere, the ambient ocean water is incredibly highly corrosive. Vent fluids contain dangerously high concentrations of dissolved toxic sulfuric acid compounds. This acidic water slowly eats away at exposed metal frames and sensors. Scientific instruments degrade rapidly in this harsh chemical fluid environment without protection. Temperature extremes pose another massive daily challenge for deep-sea mechanical engineers. The ambient surrounding ocean water rests at barely 2 degrees Celsius constantly. The dark vent fluid erupts at nearly 400 degrees Celsius violently. This massive thermal shock easily shatters normal glass camera lenses into pieces. Specialized thick quartz windows protect the delicate high-definition external cameras from cracking. The deep sea hides incredible mineral and rare undiscovered biological resource treasures. These vents constantly spew valuable heavy metals into the dark freezing water. Polymetallic sulfides accumulate slowly over thousands of quiet undisturbed years of time. These massive mineral deposits contain incredibly rich concentrations of pure raw copper. Zinc and shiny gold also precipitate from the cooling black smoke clouds. Rare earth elements slowly settle into the surrounding soft ocean mud layers. Modern human consumer electronics heavily rely on these specific rare earth metals. Industrial mining companies look toward the deep ocean for future profit margins. The East Pacific rise holds vast untouched amounts of these precious resources. Biological resources might be even more valuable than the physical raw gold. Extremophile bacteria possess incredibly unique and highly resilient cellular enzymes for survival. These complex enzymes function perfectly at extreme boiling ocean temperatures without degrading. Pharmaceutical companies study these proteins for new advanced medical treatments and cures. Industrial chemical processes use these heat-resistant enzymes to manufacture everyday human goods. The famous Taq polymerase enzyme completely revolutionized modern human genetic testing procedures. Similar undiscovered biological enzymes likely exist hidden in these Pacific vent fields. Bioprospecting involves carefully searching the deep sea for these hidden biological treasures. Scientists gently sample the thick microbial mats coating the rocky chimney walls. They carefully cultivate these strange bacteria in specialized warm surface laboratory incubators. This vital research could easily lead to breakthrough antibiotics and novel medicines. The returning water samples smell strongly of sulfur and ancient deep earth. Microbes multiply quickly inside the dark incubators aboard the gently rolling ship. DNA sequences hum quietly in the floating marine biology laboratories all night. The genetic code reveals profound secrets billions of years in the making. However, commercial resource extraction poses a massive ecological threat down here forever. Deep-sea mining could destroy these fragile ancient ecosystems completely and permanently. Heavy industrial mining machinery would crush the delicate mineral towers into dust. The resulting thick sediment plumes would choke the surrounding fragile filter feeders. Toxic heavy metals suspended in the water could poison distant healthy habitats. Conservation of the deep sea is a rapidly growing global environmental concern. The International Seabed Authority attempts to properly regulate these dark international waters. They establish complex legal rules for exploration and potential future commercial mining. Protecting the East Pacific Rise requires absolute international scientific cooperation every day. Vent ecosystems recover incredibly slowly from any major physical disturbance or damage. The freezing cold temperatures outside the vent slow down basic biological growth. A destroyed vent community might easily take centuries to fully recover naturally. Some extinct dormant vents host highly unique species found nowhere else globally. Mining these dormant vents could cause unknown permanent ecological damage and extinction. Marine protected areas are slowly being established in the vast open ocean. These invisible boundaries shield specific vent fields from greedy commercial corporate exploitation. Scientists strongly advocate for preserving these unique underwater biological laboratories for tomorrow. We are deeply connected to these strange creatures by vast deep time. The ocean acts as a vast and silent library of biological history. Each isolated vent field represents a unique chapter in this ancient book. We must protect this library from careless industrial and greedy human destruction. The Midnight Zone holds profound answers to questions we haven't even asked. The deep sea remains a beautiful realm of quiet and endless wonder. We lead the East Pacific Rise to its dark and peaceful slumber. The giant tube worms continue their silent slow dance in the currents. The blind white crabs slowly crawl across the warm rocky mineral towers. The black smoke gently rises into the freezing and heavy ocean water. The surface crew waits patiently for the bright orange floats to appear. Recovery operations often happen quietly under the dark and starry night sky. The deep ocean always finds a peaceful, steady rhythm in the darkness. Rest easy knowing the deep sea continues its steady and peaceful breathing. The hydrothermal heart of the planet beats softly in the absolute dark. The East Pacific Rise profoundly shapes our global climate. Massive amounts of thermal energy rise from the seafloor. This intense heat alters deep ocean water density constantly. At 9 degrees 50 minutes north, heat escapes rapidly. Hydrothermal fluids exit the oceanic crust at extreme temperatures. These mineral-rich fluids reach 350 degrees. This extreme heat warms the surrounding freezing abyssal seawater. The ambient bottom water sits at 2 degrees Celsius. Warmed water becomes highly buoyant and begins rising slowly. This upward movement drives global ocean thermohaline circulation patterns. Deep ocean currents transport this thermal energy across distances. The rising hot plumes mix with deep cold waters. This mixing process distributes essential chemical minerals globally today. Iron and manganese disperse into the broader ocean currents. Phytoplankton at the surface eventually utilize these deep nutrients. These microscopic surface plants produce oxygen for our planet. The deep sea directly supports surface atmospheric chemical balance. Carbon sequestration also occurs near these active hydrothermal vents. Chemosynthetic bacteria consume dissolved carbon dioxide from the water. They convert this inorganic carbon into organic living matter. Vast mats of microbes carpet the porous basaltic rocks. They lock away carbon deep beneath the ocean surface. This biological pump helps regulate global greenhouse gas levels. The dense vent ecosystems act as highly efficient sinks. Giant tube worms also store carbon within massive colonies. Rifsha pachyptila specimens grow up to 2 meters long. Their rapid biological growth requires significant carbon dioxide uptake. The East Pacific rise processes millions of tons annually. Oceanographers continue to quantify this hidden deep carbon cycle. Dr. Susan Humphreys studies these complex geochemical exchanges extensively. Her research reveals intricate interactions between rock and water. Seawater penetrates deep into the fractured porous oceanic crust. Magma chambers heat this trapped water under extreme pressure. The superheated fluid dissolves minerals from the surrounding basaltic rock. This rich chemical soup eventually erupts back into the dark ocean. The entire volume of the ocean circulates through the oceanic crust. This complete planetary filtration cycle takes about 10 million years total. The East Pacific rise accelerates this massive global water filtration system. It remains the fastest spreading tectonic ridge on our entire planet. Tectonic plates move apart at roughly 15 centimeters per single year. This rapid geological spreading creates the densest hydrothermal vent area known. Future research expeditions will target these highly active underwater volcanic zones. Scientists plan to deploy entirely new autonomous underwater exploration vehicles soon. The Sentry autonomous vehicle maps the jagged seafloor incredibly precisely today. It hovers just 50 meters above the dangerous and rocky terrain. Sentry uses high-resolution multibeam sonar to detect brand-new vents. It operates completely without a restrictive tether to the surface ship. Researchers program its complex flight path before every single deep dive. The yellow vehicle glides silently through the pitch-black ocean water. It records subtle water temperature anomalies and specific dissolved chemical signatures. Highly sensitive sensors detect faint traces of hydrogen sulfide in water. A sudden spike in chemicals indicates a nearby active hydrothermal chimney. The Jason remotely operated vehicle follows up on these robotic discoveries. Jason possesses highly dexterous robotic arms for taking very delicate samples. It streams live high-definition video directly to the surface vessel. Dedicated scientists aboard the research vessel Atlantis monitor the video feeds. Dr. Richard Lutz pioneered long-term biological monitoring at this location. He observed how vent communities recover after devastating underwater volcanic eruptions. Frequent tectonic eruptions paved the seafloor with completely fresh lava flows. These violent geological events destroy existing biological communities almost instantly there. Yet resilient marine life returns to these barren rocks surprisingly fast. Mobile deep-sea scavengers arrive within a few short dark months. Microbes quickly form thick white bacterial mats on the new lava. Young tube worms settle and grow at truly astonishing biological rates. Scientists still fundamentally question how larvae travel between these isolated vents. The active hydrothermal vents sit like tiny biological islands in darkness. Deep ocean currents must carry microscopic larvae across incredibly vast distances. Researchers use specialized acoustic Doppler current profilers to track moving water. They carefully measure the speed and direction of deep abyssal flows. Genetic testing reveals hidden biological connections between distant hydrothermal animal populations. Future deep-sea missions will drill directly into the ocean crust. The deep subterranean biosphere remains largely unexplored and completely unknown today. Hardy microbes live inside the solid rocks far below the seafloor. They survive in microscopic geological fractures filled with superheated toxic fluids. Advanced drill ships will extract cylindrical core samples from the crust. These rocky cores will reveal the true extent of subterranean life. Scientists estimate massive unseen biological biomass exists within the Earth itself. The East Pacific Rise offers an absolutely perfect scientific testing ground. The oceanic crust here is incredibly thin and highly physically fractured. Geothermal heat gradients change rapidly within the upper basaltic rock layers. New modern fiber optic cables will create permanent deep ocean observatories. These long cables will provide continuous electrical power and data transmission. High-definition cameras will monitor active hydrothermal chimneys 24 hours. Sensitive seismometers will detect the faintest underground tectonic tremors almost instantly. Advanced chemical sensors will track fluid composition changes over long periods. This continuous data stream will completely revolutionize modern deep-sea biology. We will proudly watch slow geological processes unfold in real time. The deep ocean environment will no longer remain completely shrouded in darkness. Human scientific curiosity brings bright light to these hidden abyssal plains. Every single new discovery generates even more fascinating and complex questions. The sheer wonder of deep-sea exploration remains truly and deeply profound. We send complex machines into crushing pressures to seek valuable scientific knowledge. At 2,500 meters down, the physical pressure is immense. 250 atmospheres press heavily against the thick titanium submarine hulls. Yet extremely delicate organisms thrive perfectly in this harsh alien underwater environment. They completely defy our traditional scientific understanding of absolute biological limits. The East Pacific Rise shows us life's incredible and unyielding natural resilience. Life adapts perfectly to highly toxic chemicals and boiling water temperatures there. It always finds a miraculous way to flourish in absolute pitch darkness. These deep ecosystems operate completely independently from the warm sun above us. Protecting these utterly unique biological hotspots is absolutely crucial for our future. Commercial deep-sea mining currently poses a massive significant threat to vents. Various companies seek to harvest the mineral-rich hydrothermal chimney rock structures. Active black smokers contain unusually high concentrations of valuable copper and gold. Heavy mining operations would destroy these fragile biological communities completely and forever. The thick sediment plumes from mining would easily smother nearby delicate life. Biological recovery from such immense mechanical disturbance could easily take many centuries. International marine protected areas must legally safeguard these unique deep underwater habitats. The United Nations currently debates comprehensive deep-sea environmental conservation laws globally. Dedicated scientists advocate strongly for strict and comprehensive environmental protection measures today. We must actively preserve these pristine deep environments for future human generations. The deep dark ocean truly belongs to the entire global human community. It represents the very last great unexplored wilderness on our blue planet. Understanding these deep ecosystems helps us understand our own mysterious biological origins. All life on Earth may have originally begun at deep hydrothermal vents. The abundant chemical energy here mimics early planetary conditions absolutely perfectly today. Ancient microbes found here resemble the oldest known fossil records on Earth. Protecting the East Pacific Rise essentially protects our precious shared planetary heritage. We warmly invite you to deeply appreciate this hidden watery alien world. Imagine the silent cold currents drifting slowly across the dark ocean floor. Picture the towering mineral chimneys venting thick dark smoke into the abyss. The surrounding water shimmers beautifully as extremely hot and cold fluids mix. Ghostly white blind crabs scuttle carefully across the jagged and sharp basalt. Giant red-tipped tube worms sway very gently in the deep currents. Golden deep-sea mussels cluster tightly around the warm fluid rock cracks. Pale pink eelpouts swim incredibly slowly through the dense biological vent communities. The deep sea operates entirely on its own ancient and slow rhythm. It remains completely disconnected from the frantic and loud pace of humanity. The dark abyss offers a deeply profound sense of ultimate quiet peace. You can safely let your tired mind drift into this calming darkness. The steady rhythmic flow of deep ocean currents brings quiet mental calm. Cold heavy water moves slowly along the vast and rugged mid-ocean ridge. The immense physical weight of the ocean creates a deep physical stillness. You remain perfectly safe above this incredible and hidden underwater vent world. Your own breathing can easily match the slow oceanic tidal rhythms now. Inhale deeply as the imaginary deep currents rise upward toward the surface. Exhale gently as the freezing cold water settles down quietly and peacefully. Feel the deeply peaceful weightlessness of the vast and dark abyssal plain. Let completely go of the busy day and its many stressful demands. The deep ocean continues its ancient rhythmic cycles without any conscious effort. Geological time moves incredibly slowly in the pitch-black deep-sea environment. Massive tectonic plates shift merely millimeters over many long and quiet months. Dissolved minerals crystallize onto tall chimneys atom by single microscopic atoms slowly. This incredibly slow biological pace invites you to relax your body completely. There is absolutely no rush in the deep and dark ocean environment. Everything unfolds exactly as it naturally should in the cold deep dark. The East Pacific Rise will continue venting quiet heat into the water. The giant tube worms will continue their silent and steady biological growth. The microscopic bacteria will continue processing deep minerals in the absolute dark. You can safely leave your active waking thoughts far behind you tonight. Our long scientific journey to the East Pacific Rise quietly concludes tonight. We slowly and gently ascend toward the calm ocean surface far above. The surrounding water transitions from pitch black to a deep, soothing indigo. The immense crushing pressure gradually releases as we drift upward through water. We quietly leave the hydrothermal vents to their silent and peaceful existence. The robotic exploration submersibles power down their bright artificial halogen diving lights. The rugged ocean floor naturally returns to its natural and absolute darkness. The scientific research vessel gently rocks on the calm surface ocean waves. Distant stars shine incredibly brightly in the clear and quiet night sky. The vast dark ocean and the cosmos reflect each other absolutely perfectly. You have safely explored the most extreme biological environment on planet Earth. You have quietly witnessed life thriving in the darkest and deepest depths. The beautiful scientific mysteries of the deep sea will always remain fascinating. Tomorrow holds brand new scientific discoveries for the global marine research community. Tonight is strictly reserved for deep rest and quiet, peaceful mental reflection. Let the gentle rhythmic rocking of the ocean waves soothe you completely. Allow the deep sea currents to wash away all your physical tension. The vastness of the ocean holds infinite and deeply calming natural energy. Close your tired eyes and gently embrace the quiet dark night now. Thank you for watching our deep sea exploration documentary with us tonight. We wish you a very peaceful night and beautifully calm sweet dreams.